Rex and lightning scatter on 23 SEMS. Over to you.
Thank you, Justin. And I guess lightning scatter was totally fortuitous when I first ran into lightning scatter with Brodie Churchill. In fact, we were doing tests, but Brodie lives in near Wonthaggi in southern Victoria, and he and I do tests on 1296 troposcatter fairly frequently. And this day, oh dear. This day, he reported getting what looked like meteor pings. And I got one meteor ping, which is this one here, and you'll notice this large spike here, and it equates to this little, very short ping on the Q65. Now, I knew meteor scatter doesn't work at 1296, and it turned out that there was, at the time, although I didn't know it, a very major lightning storm. But I did remember that lightning can scatter VHF. And I said to Brodie, well, let's try going to MSK 144, which is really a meteor scatter mode, to see how that will work. And we started exchanging information. So it did work. And you wouldn't expect a meteor scatter mode to work on troposcatter, particularly over 500 kilometres, because it's while a sensitive WSJT mode will work down to -30, a meteor scatter mode's lucky to work below about -5. And you can see here the signal strength reports varying up to +15 dB, occasionally getting a negative decode. And we did complete a QSO. As it turned out, we kept going, and we thought we completed 4 QSOs, and we were doing it on 2 meters at the same time. After the event, we'll go on to what happened on 2 meters. Now, it turned out that this was one of the biggest lightning events that's ever happened in this area. And this was something that one of the power authorities in Victoria put on the web to explain why the power went out. And there were some 544,000 lightning strikes over the day. In this whole area, which were sort of roughly covered between me and Brodie in southern Victoria. So there was a good explanation to why it actually worked on this day, but we thought, well, we're never going to repeat this, but we have. So this was the 13th of February, and that was our first attempt where we did complete a QSO. And you can actually go back into a lightning tracker and look at historical maps, which we've done here. And you can see these bands of lightning moving across. And the path between Brodie and I, he's slightly off the map up here. And of course, we need the lightning to be roughly in between. It's a bit like the aircraft scatter situation. You've both got to be able to see the aircraft or both see the lightning. And it worked. Now, this is a typical example where I've compared aircraft scatter, which actually did occur at the same time, with a lightning ping. And you can see the lightning ping is very short and very sharp, and the aircraft scatter is sort of just running along pretty consistently and much weaker. So I can tell the difference between aircraft scatter and lightning scatter. As it turned out after the event, while we thought we completed 4 QSOs, 3 of them were actually affected by aircraft scatter, and therefore, while they were partly lightning, they really didn't count as a lightning scatter QSO, but 1 did. Now, this is the complete set of decodes, and the black ones are all lightning, and the red ones, which all occurred with a single aircraft pass over about 3 minutes, were all aircraft. But unfortunately, at the time, we didn't know that the aircraft were causing these decodes. When we plot the Doppler shift, you can the red ones are the aircraft scatter, and they've got very little Doppler shift because the path is the aircraft between Hobart and Melbourne fly almost in line with the path, so the Doppler tends to cancel. But the lightning had a gradually dropping Doppler, and then there was a gap and another burst of lightning. So there's some clues about Doppler and lightning that still need to be disentangled. Here's the signal strength. The aircraft scatter tends to decode at a weaker signal level, down to about -6 on MSK. And that's because MSK can not only decode a single burst of signal. Each burst of signal transmitted by MSK 144 is about 70 milliseconds, but it can actually get about another 6 dB by adding up multiple or averaging over multiple decodes or multiple transmission periods. So with aircraft scatter, you've effectively got continuous scatter periods. So the aircraft scatter does go weaker than the lightning scatter, but you can get decodes off a single period with lightning. Well, the best we got was -2. Now, we were doing this on 144 at the same time, and we thought we completed a QSO on 144, but after we looked at things, all of the only decodes we got on 144 were at the same time as there was aircraft. So effectively, we got absolutely nothing on 144 and all these on 1296. Here's an example of a double decode, and there's quite a few times where we get 2 decodes in the same period fairly close together, which seems to be a characteristic of lightning. Now, this is an example of Brodie's decodes. These are very short. You can see the lightning there and there. One of the characteristics of Brodie's wavefiles is there's a whole lot of noise at the lower end of the lower frequency. Now, this is a little problem with the IC9700. In its standard configuration, the widest bandwidth is up to 3 kilohertz, but you can adjust it up to 3.6 kilohertz. But when you adjust it up to 3.6, there's a peak occurs at the bottom of the frequency range. It'd be nice if Mr. ICOM could fix that. It would also be nice if he could extend the bandwidth in the SSB mode up to the 4.5 kilohertz that WSJT is capable of using. That's particularly useful for auroral scatter where you get lots of Doppler shifts. But despite this peak at the bottom, or this bump at the bottom, Brodie was still getting decodes, but I would suggest that if you're doing lightning scatter, keep the bandwidth as high as you can without getting this bump, which means set it to about 3.2 kilohertz is about the limit. This is an example of a lightning ping, and then I've looked at it in Audacity, and you can see that the horizontal scale is expanded. You can see that it doesn't have an enormously fast or peak rise at the start. You know, you'd think that a lightning ionization would be enormous at the start and decay very quickly, but that doesn't show up on the signal strength, and there's a reason for that, which I will go on to shortly. The other problem that Brodie's got is there's a strong signal, and you can see it's hit his AGC. So it's important to turn off AGC if you're doing this stuff. Other reports of lightning scatter, as far as I can find, there's been no evidence of a lightning scatter QSO both ways, but there are 2 hams who've reported the measurement of lightning scatter, one using a 432 meg beacon, F6AGR, back in 2005, and another using a high-power UHF TV station. But of course, while they could detect that there was lightning, they couldn't have a QSO with these methods. Now, at 432, he reported durations up to several hundred milliseconds, and at 1296, I didn't see anything more than about maximum of 200 milliseconds. And at high-power UHF, I'm not sure what frequency that is, he's reporting 0.1 to 0.6. So there's some evidence that the length of the pings reduces as you go up in frequency, and that's similar to what happens with meteor scatter, that if you go from 6 meters to 2 meters, the length of the pings drops off. Now, F6AGR published this paper back in 2005, which he called Lightning Scatter, a Faint and Rare Mode of Propagation. It is certainly rare, but with digital modes, it starts to become a viable mode rather than a very faint mode. Of course, he didn't have access to MSK 144 back in 2005. Now, I suspect he's got a very strong scientific background, because he gave us some formulas like this. And essentially, the frequency at which scattering will occur increases as a square root of the number of electrons or the amount of ionisation. And the way I take this formula to mean is if you've got enough ionisation for it to occur, having more ionisation doesn't make it any stronger. There's just a step function that you get to. And I think this is why you don't get a massively strong signal at the start followed by a decay. He also reports that the diameter of the lightning channel is only a few centimetres in size, and that 80% are cloud-to-cloud type. Now, because they're cloud-to-cloud, essentially it means they're horizontal, and if you take the aircraft scatter analogy, if you can have a fairly thin horizontal channel, you will get a very broad vertical lobe, but a very narrow horizontal lobe. This guy says that you can get the fascias up to 60,000 feet. Now, we use aircraft scatter typically up to about 900 kilometres with aircraft at 40,000 feet. Occasionally, we've got reports of aircraft scatter over 1,000 kilometres, and that's generally when there's a duct feeding into the aircraft scatter. But at 60,000 feet, we should certainly be able to do lightning scatter over 900 kilometres. In fact, well over. And he says each lightning burst has two components to it. A 30 microsecond burst, which is the noise you hear on HF. And then that's followed by the ionised channel scattering the signal. I have never seen that 30 microsecond burst at 1296. I'm not sure whether that's just the bandwidth problem of using WSJT, and 30 microseconds is probably just too fast to be evident. If we take an aircraft forward scatter analogy, you get a 19 dB forward scatter gain at 1296 compared to 144, and this might explain partly why we're not seeing these lightning scatter pings at 144. Although I should say, talking to a few hams, they have seen what they believe is lightning scatter at 144 over short distances, basically sort of Canberra to Sydney, a storm goes through and they're using SSB and they suddenly hear a little peak signal. And over short distances, of course, you've got inverse square law to the scattering point and inverse square law away. So you'll get much stronger signals over short distances, which might explain that. Now, because the beamwidths at 1296 on aircraft scatter, the aircraft is multiple wavelengths, and that produces a very narrow beamwidth, and that's why on aircraft scatter at 1296, you're relying on some of the narrower components of the aircraft, the wings, to actually get enough beamwidth for it to bend back to the Earth. That's why 1296 is more difficult than it is at 144. I mean, it still works, but in the lightning scatter situation, if you assume you've got a very long ionised path, and it's all horizontal, it'll have a very broad vertical beam width, and so you don't actually lose it by going to 1296 as you do at 144, as you do with aircraft. Now, I was interested in forecasting when lightning might be useful to us. And my grandson lives in Devonport, and that's pretty close to where I need the lightning. So I said to him, every time you see lightning out to sea, let me know. And he sort of looked at me quizzically and said, Pa, why don't you just use an app? Well, see, I came from days before apps. I think Gavin, where's Gavin? Gavin will remember when this grandson was born during a GIPSTEC event, don't you? He's now 22. So the advantage of this app is it gives you an alarm every time there's lightning between in a defined circle, which you can set. And as a result of setting that, we actually got another event on the 1st of April, a much weaker event. We didn't complete a QSO, but we did get something like about 7 decodes. And this is what, when you look back historically, this band of lightning looked like. I wasn't not expecting we're going to get this very often. But then on the 24th of August, which is a bit of a surprise because I wasn't expecting lightning in the winter. I was expecting that in Tassie, it's only, you see lightning in the summer and thunderstorms. This is what we saw on the lightning tracker. And this was actually by far our best event in that we actually got 4 completed QSOs, with none of them being affected by aircraft scatter. And the shortest one actually got through in 3.4 minutes from the time of detecting the both call signs and the grid to the RRR, which is where an official QSO is completed once confirmation is exchanged both ways. So it is looking like lightning scatter might well occur far more often than I had previously expected, particularly if you use your grandson's app. Now, this was all of the lightning pings on that second event compared to, you can see the lightning moving across and the signal strength was all pretty similar. Some of it got down to -5 on the WSJT scale. And the Doppler on this occasion fell away fairly consistently, both with what Brodie detected and what I detected. So there's something to learn about what causes this Doppler. Now, I looked at the Bureau of Meteorology website to see where the best place to do this would be. And by far the worst place to do it is Tasmania. The best place would be up here. But people in, say, Brisbane, and they should be pretty much up for it. One of the problems is a lot of people start, when there's lightning around, unplug their antennas, and so that might be an issue. But I actually think it happens far more often in other places. So I find no evidence that anyone's completed a QSO before, and we've now completed 5. These are probably the first ever QSOs via lightning scatter. 1296 is a better band than 2 metres, and I can't fully explain that. Well, the propagation is rare. If you use the lightning scatter apps, it appears it might occur a couple of times a year in Tasmania and Victoria.
I have one question for you, Rex.
Yes.
Power and antenna. What were you using?
Oh, yeah, I'm using a 33 element single Yagi.
Okay.
And Brody's using, I think, a 35 element. He's using 50 watts, and I'm using 120.
Okay.